Right now, in at least 4 separate locations around the planet, the ground is rising, swarms of small earthquakes are shaking the surface, and scientists who study these systems for a living are watching more closely than they have in years. This isn't disaster movie speculation. This is happening in real published research, tracked by government monitoring agencies in multiple countries, using instruments buried in the ground beneath some of the most dangerous geological structures on Earth. And by the end of this video, you're going to understand exactly which supervolcanoes scientists are actually paying attention to right now, what's different about this moment compared to their normal decades-long background hum, and why researchers keep describing what's happening as neither an emergency nor something to ignore. Let's start with what actually makes something a supervolcano, because the word gets thrown around loosely and the real definition is more specific than most people realize. A supervolcano isn't just a big volcano. It's defined by the scale of its largest possible eruption, an explosive event capable of ejecting at least 1,000 cubic kilometers of ash, rock, and debris in a single blast. For comparison, that's roughly 1,000 times larger than the eruption that devastated Mount St. Helens in 1980. There are approximately 20 known volcanic systems on the planet capable of producing an eruption at that scale, and rather than towering peaks like the volcanoes we're used to picturing, most of them look like enormous, gently sloping depressions in the landscape, called calderas, sometimes dozens of kilometers wide, formed when a previous super eruption caused the ground above an emptied magma chamber to collapse in on itself. Here's the first place scientists are watching most closely right now, and it might surprise you that it isn't the one most people have heard of. Before we get there, it's worth understanding how these underground systems actually manage to stay molten for so long in the first place, because that's part of what makes them so hard to fully predict. Supervolcanic magma chambers are continuously fed fresh material rising up from the mantle, and that constant supply of heat softens the surrounding crust, making it pliable rather than brittle. That pliability is actually crucial because it allows the ground above to stretch and slowly inflate to accommodate new magma without immediately cracking apart, which is precisely why these systems can absorb enormous volumes of fresh material over tens of thousands of years without leaking it out in smaller, more frequent eruptions along the way. Eventually, once the magma reservoir swells past a critical volume, the crust above becomes genuinely unstable. Ring-shaped faults form at the surface and begin unzipping downward, and once those fractures finally reach the magma chamber itself, the entire central block of crust collapses under its own weight like a piston sinking into the ground, releasing the built-up material in the kind of catastrophic blast that carves out a caldera in the first place. Just west of Naples, Italy, sits Campi Flegrei, a 13-kilometer-wide caldera that sits directly beneath the port town of Pozzuoli and reaches into the edges of one of Europe's most densely populated urban areas. Roughly 500,000 people live inside its high-risk zone, and as many as 3 million people live within range of a significant eruption. Since 2005, the floor of this caldera has been slowly rising, and it hasn't stopped. Ground uplift has now passed 1.4 meters, and that rise has come paired with almost constant swarms of small earthquakes. In February 2026, alone, monitoring stations run by Italy's National Geophysics Institute recorded around 70 earthquakes in a single week, with magnitudes reaching as high as 3, 5, concentrated beneath the towns of Pozzuoli and Agnano. Just months later, on May 21, 2026, a magnitude 4. 4 earthquakes struck the region, part of a cluster of more than 1,200 separate seismic events recorded over the preceding weeks. That's not a typo. 1,200 individual earthquakes in a matter of weeks, in a region where roughly 500,000 residents live directly on top of the system generating them. This isn't Campi Flegrei's first brush with modern unrest either. The caldera experienced a similar bout of activity back in the 1980s, serious enough that thousands of residents in Pozzuoli were temporarily relocated at the time, and it has spent much of the decade since in a comparatively quieter state, punctuated by smaller episodes before the current phase of accelerating uplift and seismicity began taking shape. That history matters because it's part of why Italian authorities are treating the present unrest with genuine seriousness, rather than dismissing it as background noise. Evacuation exercises have already been scheduled for residents in the highest risk zones, and one geologist who has studied the caldera for years has publicly stated that continued unrest only increases the odds of eventual eruption, urging authorities to stay prepared regardless of how gradually the situation continues to unfold. What's genuinely new here isn't just the shaking, it's what researchers have found underneath it. A study published in the journal Communications, Earth and Environment, led by researchers at the University of Pisa and Germany's GFZ's Helmholtz Center, identified something called very long-period seismic resonance signals deep beneath Campi Flegrei. In plain language, these are specific vibration patterns that point to fluid-filled structures connecting the deep magma source directly to surface gas emissions at the Solfatara crater, one of the bubbling sulfur-smelling vents that dot the landscape above the caldera. That's a genuinely important distinction because it tells scientists this isn't just surface-level shaking disconnected from what's happening deep underground. There's an actual physical channel linking the two. The Italian government has taken this seriously enough to earmark 500 million euros, specifically for safety interventions, building reinforcement, and evacuation infrastructure for residents living in the highest risk zone. And separate modeling published in Nature Communications, examining 75 years of unrest at this same caldera, found that reinforcing buildings against seismic damage is the single most effective near-term strategy available, regardless of whether an actual eruption ever happens. Some researchers have even projected, cautiously, that the current pace of acceleration could reach what they call a critical mechanical threshold sometime between 2030 and 2034, though they're explicit that reaching that threshold wouldn't necessarily mean an eruption. It could just as easily mean new fractures forming, increased gas venting, or localized ground failure. A genuine change in the system's behavior without a catastrophic outcome. Now let's talk about the one most people already have some image of in their head, Yellowstone. Sitting beneath the most visited national park in the United States, Yellowstone's caldera stretches roughly 72 by 55 kilometers, making it the third largest caldera on land anywhere on the planet. It has produced 3 confirmed super eruptions over the past 2.1 million years, and it sits at the tail end of a volcanic hotspot track that stretches nearly 700 kilometers across the Snake River Plain, marking where the North American continent has slowly drifted over a stationary plume of heat rising from deep within the Earth. As of the most recent monthly update from the United States Geological Survey's Yellowstone Volcano Observatory, dated July 1, 2026, the system remains at its normal alert level, with background seismicity, meaning June 2026 saw 118 located earthquakes, the largest just a magnitude 2. 4 and continuous GPS monitoring shows no significant uplift or subsidence of the caldera since December 2025. In other words, right now, Yellowstone is behaving. That doesn't mean nothing is happening beneath it. It means whatever is happening currently falls within the range scientists consider normal background behavior for this specific system. And this is actually one of the most important things to understand about supervolcanoes as a category, because it directly explains why Yellowstone, Campi Flegrei, and a couple of other systems we're about to cover are all showing some degree of activity at the same time, without that meaning multiple simultaneous catastrophes are brewing. There's a concept in volcanology called resurgence, described memorably by Professor Sean De Silva, a supervolcano expert at Oregon State University. as, in his own words, the after-party after the big dance. After a system produces a massive super-eruption and its magma chamber empties out, causing the ground above to collapse into a caldera, the story doesn't end there. Fresh magma continues rising from deep within the mantle, slowly refilling and reheating the system over tens of thousands of years, causing the caldera floor to inflate and triggering exactly the kind of earthquake swarms we've been describing. Campi Flegrei, Yellowstone, Long Valley in California, and Toba in Indonesia are all currently sitting in this resurgent stage, and researchers are clear that ground deformation and earthquake swarms are, on their own, considered fairly normal behavior for a system in this phase. The genuinely hard scientific question isn't whether these systems show activity, it's figuring out precisely when normal resurgent behavior might be shifting into something that actually signals an approaching eruption. Let's go somewhere most people watching this have probably never heard of, because it's one of the strangest stories in modern volcanology. Deep in the central Andes of Bolivia sits Uturuncu, a volcano that hasn't erupted in roughly 250,000 years and is, by every conventional definition, dead. Except it isn't behaving like it. For decades, satellite radar and GPS surveys have shown the ground around Uturuncu deforming in a strange, distinctive shape researchers call a sombrero pattern, with the center of the system rising while the surrounding area sinks. Add in frequent earthquakes and plumes of carbon dioxide gas escaping from the surface, and you get a volcano that scientists nicknamed the zombie volcano. Technically dead, but still showing every outward sign of being disturbingly alive. A study published in the Proceedings of the National Academy of Sciences in 2025, involving researchers from Oxford, Cornell, and the University of Science and Technology of China, finally cracked open why. Using signals detected from more than 1,700 individual earthquake events, the team built what's essentially a three-dimensional CAT scan of the shallow crust beneath the volcano. What they found is that Uturuncu's unrest isn't being driven by magma actively rising toward the surface, the scenario that would raise genuine eruption concern. Instead, it's being driven by the movement and accumulation of liquids and gases within subsurface reservoirs, essentially fluid and gas shifting around within the plumbing system without fresh magma pushing upward. One of the study's co-authors put it plainly, stating this specific unrest carries a low likelihood of leading to an imminent eruption. So the zombie volcano's twitching, it turns out, isn't the volcano coming back to life in the way that phrase implies. It's more like aftershocks in the plumbing rather than a heartbeat starting back up. But the technique itself, this high-resolution imaging approach, is now being described as a potentially powerful new tool for reading the internal state of other restless volcanic systems around the world, and possibly even for locating valuable mineral deposits tied to the same underground fluid networks. There's a similar story unfolding in Chile at a volcanic field called Laguna del Maule, which has been inflating at an exceptional rate since 2007, among the fastest rates of ground uplift documented at any volcanic system on the planet. A study published in Geophysical Research Letters in early 2026 used nearly 2 decades of GPS and seismic data to map the relationship between this ongoing uplift and the earthquake activity surrounding it, giving researchers one of the most detailed long-term pictures available anywhere of how a resurgent supervolcanic field actually behaves over time. Just like Uturuncu, the driving question isn't whether something is happening beneath Laguna del Maule, clearly something is. It's whether this specific pattern of deformation and seismicity is heading toward an eruption, or is simply the system's long-term resurgent behavior playing out on a geological timescale that vastly outpaces a single human lifetime. Back in the United States, there's a fourth system worth knowing about that rarely gets the attention Yellowstone does, despite sitting in one of the country's most seismically active regions. Long Valley Caldera in eastern California has shown its own signs of unrest for decades, including ground uplift and ongoing geothermal activity that together suggest magma is still moving somewhere beneath the surface. Researchers describe the likelihood of an eruption there as low to medium, a step above some of the more dormant systems on this list, but still far from anything resembling an imminent threat. And halfway around the world, researchers tracking global supervolcano risk point to two additional systems worth watching for very different reasons. The Taupo volcanic zone in New Zealand and the Ira caldera in Japan, home to the frequently active Sakurajima volcano, are considered among the more likely candidates for renewed activity simply because of how frequently smaller eruptions and unrest already occur in and around them, even though a full supereruption from either remains a comparatively rare, longer odds scenario. Meanwhile, Toba in Indonesia, the site of one of the most catastrophic eruptions in human prehistory, roughly 74,000 years ago, continues to show evidence of a magma chamber slowly recharging deep beneath the surface, a process researchers at the University of Cambridge have been tracking as part of the same broader resurgence pattern seen at Yellowstone and Campi Flegrei. So here's a question worth sitting with for a second. If Yellowstone is currently quiet, and Uturunku's unrest has been explained as gas and fluid movement, rather than fresh magma, why are scientists still describing this as a moment worth paying close attention to at all? The honest answer researchers give is genuinely humbling. Fieldwork on past super-eruptions, particularly at Toba in Indonesia, has shown that warning signs before the biggest eruptions in Earth's history can be minimal, offering surprisingly little advance indication that a world-altering event was actually approaching. That's precisely why continuous, dense monitoring networks matter so much for systems like these, not because scientists expect an eruption tomorrow, but because the entire value of this research lies in learning to tell the difference between decades of ordinary resurgent noise and the specific signature that might precede an actual escalation, using data collected patiently over years and even decades before any such transition might occur. Let me ask you something directly, because I'm curious how this lines up with what you already knew coming into this video. Before watching this, had you heard of Uturunku, Laguna del Mal, or Campi Flegrei, or was Yellowstone the only name on your radar? Tell me in the comments, because I think a lot of people assume there's really only one supervolcano worth worrying about, when in reality there's an entire quiet global network of these systems being tracked simultaneously, each with its own story and its own specific reason scientists are watching it. It's worth being clear about what an actual super-eruption would mean, because understanding the stakes is part of why this research matters so much, even when the near-term risk stays low. If a system the scale of Yellowstone or Toba erupted at full historical intensity, computer modeling suggests it could drop global average temperatures by up to 4 degrees Celsius, with much sharper drops of up to 7 degrees across land and more than 10 degrees across central regions of continents like North America. Sulfur gases lofted into the stratosphere would linger for years, driving what scientists call a volcanic winter, with widespread crop failures and disrupted weather patterns worldwide before temperatures gradually recovered over roughly 2 decades. Campi Flegrei's largest eruption, 36,000 years ago, wasn't quite large enough to technically qualify as super, and it still scattered ash across the entire Mediterranean and dropped temperatures across Eastern Europe by as much as 9 degrees Celsius. These aren't localized disasters. They're events with the demonstrated potential to reshape global climate and agriculture for years at a time, which is exactly why researchers treat monitoring these systems as a genuine, ongoing scientific priority rather than a fringe concern. Here's the perspective worth carrying away from all of this. None of the researchers working on these systems, from Naples to Wyoming to the Bolivian Andes, are describing an imminent, near-term eruption at any of these locations. What they are describing is a genuinely active, ongoing scientific effort to understand systems that remain, even with modern instrumentation, only partially understood. Every earthquake swarm at Campi Flegrei, every GPS reading confirming Yellowstone's continued quiet, every fluid movement model built from Uturuncu's strange seismic signature adds another data point to a decades-long project trying to answer one of the hardest questions in Earth science. How do you tell the difference between a supervolcano simply breathing? In the ordinary sense, that word can apply to a resurgent system, and a supervolcano actually waking up. It's genuinely remarkable how much monitoring infrastructure now sits quietly on the top of these systems, largely unnoticed by the millions of people living nearby or visiting as tourists. Yellowstone alone produces more continuous scientific data than any other volcanic system on Earth, drawing on dense networks of seismographs, GPS stations, and satellite imagery managed around the clock by the United States Geological Survey. Italy's monitoring network around Campi Flegrei is considered one of the densest geophysical arrays anywhere in the world, specifically because 500,000 lives depend on catching any genuine shift in behavior as early as possible. None of this infrastructure exists because an eruption is considered likely tomorrow. It exists because these systems have already proven throughout geological history that they're capable of reshaping the planet's climate for years at a time, and the only real defense available is patient, continuous, decades-long observation. As one geologist studying Campi Flegrei put it, the probability of a catastrophic eruption at any of these systems remains low, but it is not nil, and that combination, low probability paired with genuinely global consequences if it ever does happen, is precisely why the world's best volcanologists keep their instruments running and their eyes on the data every single day. If this gave you a clearer picture of which supervolcanoes actually deserve your attention right now, and which ones are simply doing what resurgent systems normally do, hit like, subscribe for more deep dives into the geological systems quietly shaping our planet, and tell me in the comments which one of these you want covered in more depth next. Stay curious, stay grounded, and I'll see you in the next one.